Good afternoon. I want to thank Tim and Susan for inviting me. I guess a lot of us agree that seafloor geodesy is very important. And a few years ago, I started to try to talk with physical oceanographers about how to use their expertise to help us to remove noise in these ocean bottom pressure measurements. And that resulted in a project that we did last year, that we collect some data offshore Oregon, and using these called CPIES. I'll talk more about this instrument. So a main thing I think come up with this really is by working with physical oceanographers, we can improve our understanding of these deep pressure measurements. And this echo a little bit on what Songlei talked about last night. By working with a different kind of data, okay, you're really improving your understanding. So I want to start my talk by make an analogy. Okay, on the left is a review paper by Tim 27 years ago. If you look at it, there are some spatial scales, time scales, different events. And if you look closely, there is GPS 1990. And Tim was predicting GPS 1995, kind of expanding our. So I guess we all noticed that the improvement in these geodesy measurements really revolutionized our study of geophysics. And a few years ago, Roland and David wrote a review paper on seafloor geodesy. Shown on the right, that's a panel showing about the vertical deformation. They also had a panel on horizontal deformation. So I was struck by how similar these two figures are. And I really hope that we can reproduce our success of improving on-land GPS by improving seafloor geodesy in the next 10 years or so. Okay, so yesterday Novell talked about some of the scientific motivation for seafloor geodesy, so I just skipped that. One challenge, I think, at least for these pressure measurements, is that these noise from water is as large as signal, especially when you look at source vents or loading or shallow locking. And the question is how to further reduce the noise. Okay, wouldn't it be nice if we can reduce the noise on these color lines on the right to similar as the bottom where it's on-land GPS? All right. So my proposal is to get help from physical oceanographers. That's what I've been doing for the last 2 years. All right, so CPIES is a current and pressure recording inverted echo sounder. It has a yellow float which lifts the current meter, which is that small ball in the middle. So that's a current meter. Lifted about 50 meters above the ocean bottom. And then in that white sphere, it has an echo sounder, which are used to determine the thermocline depths, and also has a parascientific pressure measurements. So you can deploy these things as OBS, okay, just free drop. And it has an acoustic release. You can recover your instrument. And they don't record, so they record the pressure about every minute. So their power price consumption is much lower than OBS. Their battery can last up to 5 years. So why we are interested? Because I think all of so in the deep ocean, there are some deep eddy processes which has a amplitude and time scale and length scale that similar to our interest, for example, source events. So on the right is a figure showing one of the snapshot of the pressure system in Kuroshio offshore Japan. And on the left, these are detected drifted pressure measurements at one station of this array. Okay, on the bottom, it's a 3-day low-pass filtered. You can see these, the magnitude. So HPA is a very convenient unit. So 1 HPA equals to 1 centimeter of water thickness. So there are 20 centimeter variation in deep pressure. All right, so one way to think about is ocean as having a weather system, right? When you have a low pressure, high pressure system where things started to move. So on the land, wind started. On the ocean, you got deep ocean currents. And all these currents flow, and also wind flow along these isobars, right? And the strength of these currents and wind is proportional to the pressure gradient of the system. So if we can map the pressure and the currents, you are able to recover or model these systems. So URI, the physical oceanographer group, really have been doing this for more than 20 years. And here are a few sites have deployed their CPIES, or sometimes just PIES without a current meter. There are 3 most recent deployment, one in Gulf of Mexico, one in Drake Passage, one in Crucial. And mostly, sometimes the deployment usually lasts 1 to 4 years, and the depth is usually 3 to 6 centimeters, but they can go shallow. So this really is a 2-dimensional problem. So you really need a 2-dimensional array to map these processes. So here are some of the examples of the array design. Right? They have different coverage and spacing, but you really need a 2D system to map this. So here is a animation from the Crucial experiment. So here is a daily average pressure system for 1.5 months. And the color shows the deep pressure. So the red is high pressure, the blue is low pressure, and the arrows show the current direction and also the strength scaled. So one key thing about this is current speed is proportional to lateral pressure gradient, not pressure. Right? So combined, we can map this, and then you end up with a residue of 1 to 2 centimeter accuracy in pressure. So these are really encouraging. So it kind of motivate us to try this technique in nearshore. Well, nearshore compared to their deep sea deployment. So basically in subduction zones. So last year we deployed 4 CPIES offshore Oregon, and it's supported by NSF Marine Geology and Geophysics. So the main idea really is try to quantify water contribution to pressure using this system. We have several specific objectives. For example, we want to validate our pressure measurements, and also we want to understand the processes influence the pressure and deep current in Cascadia and near the trench, and also determine if there's any source event happened. So we work closely with William Wilcock, Mark Rosenberger, Parker McGrady, and Debbie Kelly, and we talk about ideas, exchange ideas. So University of Washington has established some of these benchmarks along offshore Newport. These green squares are their benchmarks. So they are really looking for long-term locking. And they have pressure measurement on these benchmarks too. So we decided to deploy our CPIES, 4 CPIES, near 3 of their benchmarks and 1 between them. One of the premise or motivation really we think or expecting if we have any deformation, it should be closer to the trench, right? Okay, so first after we retrieve data, we exchange our data with University of Washington and Scripps. So first thing we look is the pressure. And the red line are the pressure measurements from our instrument, and the blue line is from either University of Washington or Scripps. So they match really well. And we didn't drift the blue line, so there is a little tilting you can see, but once we do that, it's almost identical. So that's encouraging. So the second thing is to understand these pressure. So these are the pressure measurements on the 4 sites we have. So immediately you can see there is some common mode direction. This dominate these measurements. And again, the unit is HPA, so 1 HPA is 1 centimeter. So at any site from peak to trough you're looking at about 10 centimeter of variation. All right. So we have some hypotheses on this. So one of the main thing is these common mode could come from a locally or remotely wind-forced process, which has a very large spatial scale. If you think about these pressure system, the baseline of our array is only 20 kilometers. So the one possibility is we are mapping these red bar. It's just for comparison, right? So we won't see these. So we'll see this common signal, right? And there are numerical models we can look into to confirm this. That's what we'll do next. So there are different ways to remove these common mode signals. One of the simplest way is assuming the station you measured offshore, the 01, which we think is on the other side of the trench, shouldn't have any tectonic signal. Okay, we use that as a reference. Then we just subtract the pressure measurement from that, and then looking at the difference. So it's like difference in GPS. Okay, you take the GPS signal from 2 stations and just calculate difference. Okay, that should improve. If there is any common signal or noise in this station, you should remove it. So there are a couple of things we noticed. First, When the stations are very close, the difference is small. Okay, so that's a good thing. And the second thing is when it's longer. So for example, in the bottom, the O3 and O1, the difference is really large. We don't really fully understand this. Okay, we talk as physical oceanographers, they don't know either. So we think it is some of the coastal waves. And next, we were hoping to look at numeric models and also combine current meter measurements to understand this. So the hope is, if we can understand what they are, we know what to measure, and we can remove them. So that's really the ultimate goal. So we also measure deep currents. Deep currents are rare, okay, especially in these trenches, because I don't know. So physical oceanographers, either they are really interested in the deep ocean, or they are really interested in the shallow coastal region. So the trench really is somewhere they didn't pay attention to that much. Okay, so I think that's really an opportunity for us to collaborate. Anyway, so we were really surprised by looking at these current meter measurements. So these, each of the blue bar is 1 day average at that site. And when it's pointed up, it means most of the currents are going north. Okay, if it's pointing south, it's going down, it's going south. So first of all, the currents are weak, okay, up to 5 centimeters per second. Okay, that kind of surprised my collaborators. Second thing is when you look at through these 4 sites, so the first 2 sites they have some correlation, but when you go to O2 and O3, they look completely different. We don't really know why. Okay, so we have a number of hypotheses. Maybe there's some local processes or related to bathymetry. We don't know. Okay, but this is, I want to point out, this is one of the first in situ measurements of deep currents in Cascadia. All right. So usually, physical oceanographer will use these currents and the pressure difference to reconstruct the system, and the way it works is the speed of the current is proportional to the pressure difference. Okay, here I did an exercise just saying, okay, let's take the difference between 2 sites. For example, on the top, the magenta line showing the pressure difference between O2 and O1, all right? Then we assume the current measurements between, which is this O1.5, represent this average pressure gradient between these 2 sites. We can predict how much pressure that will create on these 2 sites, which is the blue line. So I think it's encouraging in the sense that it produces the predicted pressure magnitude-wise, it's a little slightly smaller, but comparable. And also, there are some periods you do see it matches better. Of course, there's periods they don't match better. So I think this is hopeful. Okay, we are still looking detail into these processes. Okay, but when you look at the pressure difference between O3 and O1.5 based on current measurement at O2, that's a little different because the blue line here predictions are much smaller than the real observed pressure difference. So we think O3, because it's also the shallowest site, so maybe there's something wrong. Well, it's not something wrong, but it's by some special activities that we really couldn't resolve by using these 4 sites. Okay, so we are really limited by this short 1D array. All right, so the next step, we will try to work with physical oceanographer who develop these numeric models. So here is one numeric model developed by Parker McGrady from University of Washington, and he used atmosphere forcing on the surface of his domain, and he used HICOM, which is a global physical oceanography model, as boundaries of his domain. And he can calculate pressure measurement, pressure and current in the deep ocean. Right? So we talked with him before we did the deployment, and he said he was very comfortable or confident with his model at shallow water. But in the deep water, he didn't really have much confidence because there's so rare any especially current measurements. All right, so we compare our in situ results with his model. So on the left, these are pressure measurements. On the right, these are current measurements. And the red lines are our measurements, and the blue lines are model output. They're all filtered the same way. So I think I will say that the physical numeric models is realistic, which means if you look at the wiggles And also, we also did a frequency analysis. Seems to the dominant processes have similar frequency as our observation, right? So it's realistic, but the problem is it's not real. You can't really use it to correct a water contribution to pressure, right? So next step, what we plan to do is look more detail about his models and also compare our measurements, try to understand really the process, okay? So last objective we have is there any source vents? Maybe. Okay, the reason I said that is because we, in our pressure sensors, have a drifting problem, all right? So the drifting is a well-known problem in all these parascientific sensors where you might, if you don't remove it correctly, it will introduce some bias. So this magenta line here is the pressure difference between O3 and O1, all right? There's some wiggles. If you're looking at that, you don't see, you wouldn't see there's a step. However, if I tilt it a little bit in the bottom, all right, and you can draw lines, you see, hey, is there in 2 centimeter source vents? Maybe. And if you look at duration, it's 10 days. Okay, sounds good. So I think it's really challenging to definitely or determinatively to look for source vent just using these drifted sensors. There are a number of ways you can get away with it. So one way is to do the experiment in a place where you have on-land GPS that are close enough, can tell you there is an event. For example, in New Zealand or Costa Rica. Okay, if you know, with that information, you can do much better with the drift, all right? The second approach will be develop some kind of zero drift sensors. And there is one under development by William Wilcock and Mark Zumberger. They had some success where they can limit the drift to a few millimeter per year. But it's still a work in progress. All right, so to conclude, I think the east boundaries, in our case Cascadia, really introduce some new wave system processes that is different from the deep ocean, where we really need to understand. But in our case, we are really limited by these short one-dimensional array at CPIES. Using CPIES as Cascadia, and there is no concurrent OBS deployment. We think the combination of in-situ physical oceanography measurements and numeric model is key to advance our understanding of the ocean-bound pressure, and we should work with them. A group of us tried to propose to do an experiment offshore Costa Rica and using CPIE array. There are a number of advantages of doing it in Costa Rica. Okay, so first there are well-known shallow source vents, and the GPS stations are close enough to tell you it happens. And also there is a strong scientific motivation. In this region, there was an earthquake that didn't rupture all the way to the trench, and we want to know why, right? So in an area like this, which the spacing of these CPIES would be on the order of 25 kilometers. So in this case, we think it's really a next step we can take to really understand the potential of using CPIES to remove water signal. And I want to end so that's the end of my talk. Thank you.
Questions for Matt? I have one. The model you showed by McGrady that was paced by HICOM.
Use a microphone.
In the model that you used, that McGrady did, how many CPIES would be useful? What's the minimum number of CPIES in that region, which I think was of order 200 kilometers along the plate boundary? How many CPIES would be required to really do the job of calibrating the physical oceanography there?
That's a good question. I never thought about that. I don't know. It depends on really the spatial and temporal scale of these processes. So over here we have high-resolution models. I think in Costa Rica there's no high-resolution model, but there are global HICOM model, which I mean it's not too coarse. It's I think 1/12 degrees. So I think the point to really look at it, but I don't know the number. I had to do the calculations.